Hey everybody, this is Miss Wilson. I am the other half of the pre-calculus team here at Randallstown, and I will be reviewing Unit 2 Lesson 4 notes for Intro to Fundamental Theorem of Algebra. And before we get started with all of my explanations, what I'm actually going to have you guys do is to pause the video and write down the different definitions that you see here in front of you on the screen, because they're kind of lengthy, and in that way you can have them already written and go ahead and just follow along with me, so that way we can get into the nitty-gritty of all the important stuff. Okay, all right, so go ahead, pause me now, and then I'll be here when you're done, and then we'll go over them. All right, see you in a bit. Okay, so if you have paused me, welcome back. If not, I highly recommend that you do, or you could listen to this video in its entirety and then go back and take the notes, but I advise you to go ahead and do it first, so that way it's already done and over with and you can just follow along. So let's start by going over some vocabulary and key terms that's important. All right, so the first one is a polynomial. So that's an expression made up of multiple terms and variables. So when you have a equation like f of x equals 2x cubed plus 5x squared minus 3x plus 27, then that's going to be a polynomial. All right, so it's going to be made up of terms, it's going to be made up of variables, and there may also be some constants there. Now, let's look at a degree of a polynomial. Well, a degree of the polynomial is going to be the highest power of the variable in a polynomial. So when we refer to a degree of a polynomial, we're talking like x cubed of a third degree polynomial. So x cubed of a third degree polynomial means that the highest power of the variable in that polynomial happens to be x to the power 3. You may also see like x to the power 4. So we would call that a fourth degree polynomial. X to the power 5 is what we would call a fifth degree polynomial. So the highest degree of the variable basically names the polynomial, and it names its degree. All right. Now, when we refer to the roots and zeros, okay? So let's talk about roots and zeros for a second. Well, we often also use these words interchangeably with things like solutions or x-intercepts, right? And so what they are the values of the variable that make the polynomial equal to 0. And a lot of times we forget that. We forget that when a polynomial is equal to 0, then that means it is technically giving us its x-intercept, because y is equal to 0. And f of x is kind of just a fancy way of saying y. So if I plug in x, this value of x, out comes 0, okay? And so that's the meaning of a root or a 0. So now let's go ahead and move on to some of the bigger picture here, which is the fundamental theorem of algebra. All right. So the fundamental theorem of algebra states that every polynomial of degree n, where n is a positive whole number, has exactly n roots or zeros. And you can count their multiplicities, including real and complex numbers. All right, so this is a mouthful, but really all it's saying is if I have a third degree polynomial, then that means I have 3 zeros or 3 roots for that polynomial. If I have a fifth degree polynomial, then I will have 5 zeros or 5 roots for that polynomial, okay? And when we talk about multiplicities, that just means how many times those particular roots or zeros occur. Now, don't worry too much about the word multiplicity right now, because we're going to talk a little bit more about multiplicities in our next lesson. But really, just the overall idea here is that whatever the degree is of the polynomial, that tells us how many zeros we should be looking for. And those zeros can include real and complex numbers. If you go back to Algebra 2, you learned about complex numbers. We call those imaginary numbers, or I, and we'll talk a little bit more about these later on in this particular lesson, all right? Okay, so let's now move on to the factor theorem, all right? So the factor theorem states that if f of x is a polynomial and f of a is equal to 0, then x minus a is a factor of f of x. That's a big mouthful just to say that if I have a factor x minus 3 and I find the root of that factor, so let's say x minus 3 would be x is equal to 3, and I'm going to jot that down. So if I have x minus 3 and I set that equal to 0, well, if I add 3 to both sides, this crosses out x is equal to 3, all right? So if I take that x equals 3 and I plug that back into the polynomial or to the equation, f of x, then I can determine if it's a factor. And what will happen is it'll equal 0. So let's try that out. I'm going to go ahead and I'm going to plug in 3 for all the places where I see x. So before I do that, I'm just going to make some placeholders and then I'll come back. And if you hear Baby Shark in the background, that's because my 1-year-old is obsessed with Baby Shark and likes to listen to it on repeat over and over again. All right, so let's go ahead and plug that 3 in for all the places where you see x. So I'm going to plug in a 3 here, I'm going to plug in a 3 here, and I'm going to plug in a 3 here, okay? If you were to place this in your calculator, and I hope that you do, just for good measure, you will find that f of 3 is equal to 0. So that means that x minus 3 is a factor of f of x. Okay? So all the factor theorem means is if you were to take that factor, you take it, you find the root of that factor, and you plug that number back into the equation. If it equals 0, then x minus 3 or x minus a is a factor of f of x. Okay? All right. So now let's talk about the remainder theorem. All right, so the remainder theorem states that when you divide a polynomial f of x by a binomial in the form of x minus a, the remainder is f of a. So in other words, if you want to know the remainder, just plug in a. It's that simple. So if you want to know the remainder of something, if you just plug that number in, it'll technically give you the remainder. And that's pretty great because after learning long division and synthetic division and the area model, that's pretty helpful to figure out if there's going to be a remainder or not, and if so, what the remainder is. So again, I'm going to take the factor x minus 1, I'm going to set it equal to 0. I'm going to go ahead and add 1 to both sides so that I can get what x equals. So x is equal to 1. Now I'm going to take f of 1. So that means that everywhere I have an x, it will now be replaced with a 1. All right, so I'm going to plug in a 1 here. I'm going to plug in a 1 here. I'm going to plug in a 1 here. Pause me for a second and go ahead and plug this in to your calculator, okay? And I want you to see what answer you get. So go ahead and do that. And I'll be here when you get back. All right, so if you're back, what you would have found was that you would take these numbers. So this would be 2, this would be 3 raised to the power of 1. So this will be 3. This will be 17, and this will be 30. And then if I simplify this even further, I would get 5 minus 47, which is equal to negative 42. So what that tells me is if I take f of x and I divide it by x minus 1, then my remainder is going to be negative 42. All right? So just that simple. Okay, so now let's move on. And let's look at complex zeros of conjugate pairs. All right, so we're just kind of giving you this information because this is just one of those FYI things, which is why I wrote FYI right here, okay? So if a polynomial, so I'm reading this, the complex zeros of conjugate pairs, if a polynomial has real coefficients and a plus b times I is a 0, then its conjugate a minus bi is also a 0. All right, so it basically tells you that if you have one complex zero, because of the theorem of conjugate pairs, you will find the other one. All right, so let's just look at it. Suppose that we had f of x is equal to x squared plus 4. Find the zeros. So the solution step says, first you take f of x and you set it equal to 0. Okay, great. Let's go ahead and do that. So I'm going to take, instead of it being equal to f of x, I'm going to make it 0. And I'm going to say that's equal to x squared plus 4. All right, so step 1 done. The next step says solve for x. All right, I can do that. So in order to solve for x, I need to get x alone. So I like to draw a line just as a reminder to whatever you do on one side of the equal sign, you also do on the other. So I'm going to start by subtracting 4 from both sides. This cancels out, and I have negative 4 is equal to x squared. All right, and then I need to undo this x squared. So the way that I undo the x squared is by finding the square root on both sides. So that leaves me with, and I'm going to just reorganize it, x is equal to the square root of negative 4. Well, the square root of a negative number is what we call a complex number. All right, and so when you have a complex number, that means that we have to take the square root of negative 1, okay? And so I would have the square root of negative 4 is technically 4 times negative 1. If I broke this apart, I would have the square root of 4 times the square root of negative 1. Well, that would mean that x is equal to 2 times I, and x is equal to negative 2 times I. All right? And just to break this down even further, well, the square root of 4 can equal, let me go back one, sorry. The square root of 4 can equal 2, or it can equal negative 2. And the square root of negative 1 is always equal to I. So what the conjugate pair theorem tells me is that even if I just only found out this 2 and I, right here, x equals 2i, then this conjugate pair, negative 2i, would also be a root. And so these two solutions are called conjugate pairs. Okay? So if you feel like I'm not 100% on that, feel free to pause me and to kind of go back and review that again about the complex zeros of conjugate pairs. And remember, this is just more of an FYI, so that way if we ever talk about conjugate pairs, that you'll have an idea of what we're talking about. All right, so I hope that this lesson was helpful for you and that you were able to understand the Fundamental Theorem of Algebra, the factor theorem, the remainder theorem, the complex zeros of conjugate pairs, and how to apply those theorems into situations when working with polynomials. As a bonus, I went ahead and wrote a note summary. But I would like for you guys to see if you can come up with one different from ours. Something else that maybe you were able to pull out about the Fundamental Theorem of Algebra. But what I wrote was, the fundamental theorem of algebra is important because it's like a promise or guarantee about polynomials. You will always be able to determine the number of roots as it is equal to the polynomial's highest power. So again, for example, if I had x to the power of 3, and that was a third degree polynomial, then that means it's going to have 3 roots. All right? So again, I hope this lesson was helpful for you, and always feel free to reach out to me or to Mr. Kluwan if you have any additional questions about this lesson. And we'll see you for the next lesson, which is lesson 5, rational roots theorem. Have a good one.